Hello and welcome to part 3 of the CNC and Modular Arithmetic lecture, and this lecture will be on the Chinese remainder theorem. If you haven't watched the first two parts of this lecture series, I do encourage you to watch those. You need a good foundation on modular arithmetic to get a good understanding of today's lecture. And do note there's a handout on all of this that the lecture covers, and that will be linked in the description. So without further ado, let's go on. Mm, there we go. All right. So the Chinese remainder theorem helps us solve systems of congruences, aka these things over here, when you're presented with two congruences and you need to find the solution expressed as one congruence. Now, the Chinese remainder theorem describes a method on how to solve this, and so let's just move on with it. It's not too hard of a process, so let's start. Let's look at this congruence first of all. And this congruence, as we know, we can write this as A is equal to 3k plus 1. We know that's true because the definition of this congruence is that A leaves a remainder of 1 when divided by 3. And that is expressed by this because 3k will always be divisible by 3. And this is for some integer k, by the way. So now we can substitute this into this congruence. And this is going to give us 3k plus 1 is congruent to mod 5. All right. Now we can actually solve for k here. Subtract both sides by 1, and we get 3k is congruent to 1 mod 5. Okay, that's 3. Now, we know that we can take the modular inverse from part 2 of this lecture series to isolate k. And we know that the modular inverse of 3 modulo 5 is 2, since 3 times 2 is congruent to 6, which is congruent to 1 modulo 5. All right. Now that we have that information, we can multiply both sides of this congruence by 2, and that'll give us an isolated k, which is congruent to 2 modulo 5. Now what we're going to do now is do the same thing as we did for the first congruence. We're going to write this as an equation, and this will give us, let me pick a different color, this will give us k is equal to 5j plus 2 for some integer j. And we find this equation similarly as we did with this equation over here. All right, so what can we do with this? Well, we have two equations here, and we can actually sub k back into a. So that's going to give you a is equal to 3 times 5j plus 2 plus 1. And simplifying, that gives you a is equal to 15j plus 6 from here, and that plus 1 there, so that's plus 7. Well, remember how we wrote this equation right here? We can actually reverse that into a congruence. And we know that this equation tells us that whenever a is divided by 15, it leaves a remainder of 7. So in fact, we can actually write this as a is congruent to 7 mod 15. Now there's probably some interesting things that you've noticed. One, this solution right here is the product of these two numbers, and that is not a coincidence. That is how you get the solutions of these system of equations, since you have this 3 times 5j plus 2. Another thing to note is that the two numbers here must be relatively prime. Why must they be relatively prime? Note here how we had 3k was congruent to 1 mod 5. Well, if 3 and 5 weren't relatively prime, let's say it was 3 and 6, well then 3 wouldn't have an inverse modulo 6. So we cannot solve that congruence if uh, those two numbers over here were not relatively prime. So they have to be relatively prime for this to work. Let's move on. Since we now know the strategy, let's go ahead and just solve another one of these congruences for practice. We know that we can write A as A is equal to 6k plus 4, and we can sub that into this congruence, which gives us 6k plus 4 is congruent to 17 mod 35. Well, subtracting 4 from both sides, that gives you 6k is congruent to 13 mod 35. Well, now we just have to find the inverse of 6 since the k has this 6 in front of it. Well, we know the inverse of 6 will be 6 since 6 times 6 is equal to 36, which is congruent to 1 mod 35. All right. So if we multiply both sides of this congruence by 6, we should get k is congruent to 78 mod 35, which is actually congruent to 8 if you simplify it down, since 35 times 2 is 70. 8 mod 35. All right, so we can write uh, k is congruent to 8 mod 35 as, right here, this is k is congruent to 8 mod 35. We can write k being equal to 35j plus 8. And we can substitute that back into here. So we get a is equal to 6 times 35j plus 8 uh, plus 4. And so that's going to give you 210j plus 48 here, plus the extra 4, so plus 52 is what it should give you. And we can convert this back to congruence, and that is just A is congruent to 52 mod 210. So as you can see, the times remainder theorem can help us solve these systems with congruences. And so let's move on to see how they can help us solve some problems. All right. So here's an AMC problem for you. So in this problem, it says let n equal 1, 2, 3, 4, 5, and so on. Like basically the 79-digit number that is formed by writing the numbers 1 to 44 in order, one after the other. What is the remainder when n is divided by 45? Well, calculating the remainder of 45 may seem a bit complicated to us, but CRT, we can do reverse CRT, and we can calculate n in modulo 5 and modulo 9. Why? Because both 5 and 9 are relatively prime and their product is 45. So if we can get this congruence values here, we can actually solve this congruence for 45. Well, the modulo of 5 is very obvious to us. Clearly, it'll just be 4 since, I mean, that's basically it. It'll be 4. Dividing this whole number by 5 will give you a remainder of 4. Now, the modulo 9 one is a bit more complicated. Here's an interesting fact. A number is congruent to the sum of its digits, modulo 9. And that can be proved by the fact that 10 is congruent to 1 mod 9. And if you want to learn more about that, you can search it up in your own time. I won't cover it in today, but it basically involves splitting a number into its digits. So like 3 times 100 plus 2 times 10 plus 1, which is 321. And you can actually knock out uh, these multiples of 10 and replace them with 1 since they're congruent to 1 modulo 9. And so that gives you 3 plus 2 plus 1 modulo 9, which gives you 6 modulo 9. It's a very cool fact. So we're going to use that here. And so we want to calculate the sum of all these digits. But how do we do that? Well, note that how I said that the integers 1 to 44 in order. And, well, we know that we have some two-digit numbers, but those two-digit numbers are congruent to the sum of their digits in modulo 9. So, whereas, for example, if you were to add 40, like if you were to like take the sum of the first 44 integers, we would have a value modulo 9. Why? Because 44 is congruent to 8 modulo 9, and so is 4 plus 4 is also congruent to 8 modulo 9. So it doesn't really make a difference here since we're looking at the sum of the digits. We can just sum 1 to 44. As we know, the sum of the first 44 integers can be expressed as 44 times 45 over 2 by the formula. And if you're not familiar with it, the formula for the first sum of the first n integers is n times n plus 1 over 2. Well, here we can cancel these to get 22 here. So this gives us 22 times 45. However, 45 is divisible by 9. So that means this whole thing, this whole number is 0 modulo 9. So now we can go ahead and solve this congruence real quick. So we can let n equal 5k plus 4 for some integer k, and we can sub that into this congruence. We get 5k plus 4 is congruent to 0 modulo 9. If we subtract 4 from both sides, we get 5k is congruent to negative 4, but we know that negative 4 is congruent to 5 modulo 9. So we actually get this. Now, you don't have to go much further. Why? Because, well, we don't have to hand compute the inverse, because if we know that if we multiply 5 by its inverse, we'll get 1. So if we multiply by the inverse of 5 on the left-hand side, we'll get k, since 5 and it times its inverse cancels out. But we also have 5 here, so multiplying 5 by its inverse gives us 1. So we don't have to actually calculate the inverse, we can just calculate this directly, which gives us k is congruent to 1 mod 9. Well, now, all I have to do is write this as an equation. K is equal to 9j plus 1 for an integer j. So if we sub that back in, n is equal to 5 times 9j plus 1 plus 4, and that will give us n is equal to 45 plus 5 here plus 4 there, so that's 45j plus 9, which if we convert into congruence will be 9 modulo 45. So the remainder when you divide n by 45 will just be 9. That's a nice problem that shows you how to apply the tiny remainder theorem. So let's move on to another one. Ooh, compute 12 to the 34 to the 56 to the 78. That's a weird problem. Well, we can simplify this calculation by CRT once again. So let's let this number be n, and we can split this into modulo 18 and modulo 5. So let's look at n modulo 5. Well, this becomes, in modulo 5, it becomes 2, well, n is congruent to 2 to that exponent tower, which we will look at. I'm not going to write it all out. Actually, that's not congruent. Oops. Um, sorry, that's just bad notation by me. And that is modulo 5. Well, how do we calculate this? We gotta look at this, and if we actually look at powers of 2, modulo 5, 2, 4, 8, which is 3 modulo 5, and 16, which is 1 modulo 5. That's key. So that means every multiple of 4 modulo 5 gives us, well, it gives us 1. So if you can find the remainder, if you can find this exponent thing, modulo 4, it will tell us which one of these residues to use. If it's divisible by 4, if it's 1 mod 4, we use this residue, 2 mod 4 this, 3 mod 4 this, and 4 mod 4 this. So let's look at that. Well, 34 is divisible by 2. And if we take 2 to some power, we'll get more factors of 2, which means we'll definitely have more than 2 factors of 2. This will definitely be divisible by 4. So that means that we'll have to use this residue, which gives us that n is congruent to 1 modulo 5. And let me restate that again for those of you who may have not understood that. Well, as I said before, since this cycles, because if you multiply this by 2 again, we'll get back to 2. So this does cycle in cycles of 4. We just have to evaluate this exponent here, modulo 4. And since 34 is already divisible by 2, that means there's a factor of 2 in here. And if you raise this to some large power, we'll get that number of large power factors of 2. And since 4 is equal to 2 squared, that large number is definitely greater than 2, so this number will definitely be divisible by 4. So that's why we have this, n is congruent to 1 modulo 5. All right, let's move on with modulo 18. And now I'm just going to use a logical argument with you for modulo 18. Note that 18 is equal to 2 times 3 squared. And also note that 12 is equal to 2 squared times 3. As the same argument I was saying before, we're raising this 12 to a humongous power. That means we're going to have 2 times some humongous number of factors of 2, which means we're going to have some large number of factors of 2. And we have some large number of factors of 3, since we're raising this to that exponent, which means that this number will definitely be divisible by 18. That means we'll have 0 mod 18. Now we just have to solve the congruence. So let's try to do that real quick. So n is equal to 5k plus 1, as we know. Shove that back in here, and we get 5k plus 1 is congruent to 0 modulo 18. And that gives us that 5k is congruent to negative 1, which is congruent to 17 modulo 18. Actually, it might be more beneficial with the multiplication to keep this as negative 1. So I'll just keep it as negative 1. And now we have to find the inverse of 5 modulo 18. We can just start listing out multiples of 18 plus 1, so 19. If we add 18 to that, 37, which is 18 times 2 plus 1. This is 18 times 1 plus 1. This is 18 times 2 plus 1. And 55, which is 18 times 3 plus 1. And that is definitely divisible by 5, which tells us that 5 times 11 is congruent to 55, which is congruent to 1 mod 18, which tells us that the modular inverse of 5 modulo 18 is 11. So if we multiply both sides by 11, we'll have k isolated here, and we'll have a negative 11 over here, which gives us k is congruent to negative 11 mod 18, which is congruent to 7. Let's note that here. So that means, let me just erase this side stuff here so we have some more room to actually solve out the congruence. We actually get k is equal to 18j plus 7 from here. And if we sub that back into the expression for n, we get n is equal to 5 times 18j plus 7 plus 1, which gives us that n is equal to 90j plus 35 from here, that plus an extra 1, so plus 36, which tells us that n is congruent to 36 mod 90. And you can see why splitting this into two mods is very powerful. We just can't directly compute this mod 90. It would be quite difficult. So this is why Chinese remainder theorem is very powerful. So let me just cover, we have two more problems. One is this system of congruences. Um, I'm going to actually leave this as an exercise to you. It's basically us solving a system of congruences, and I'll come back and I'll tell you the solution. So I assume that you've tried this problem. So as you can see here, the only step to do to get this into something we know is to isolate the x's. And the only way to do that is to multiply by their modular inverses. Um, so we know the modular inverse of 2 modulo 5 is 3, since 2 times 3 is equal to 6, which is congruent to 1 mod 5. So if you multiply by 3 on both sides, we'll get x is congruent to 3 mod 5. And we can do the same thing for 7 here. Well, we have to list out, the possible ways we can get the residue. So 11 times 1 plus 1 is 12. 11 times 2 plus 1 is 23. 11 times 3 plus 1 is 34. 11 times 4 plus 1 is 45. 11 times 5 plus 1 is 56, which is equal to 7 times 8. So 8 is the modular inverse of 7 modulo 11. So if we multiply both sides by 8 here, we'll get x is congruent to 48, which is congruent to 4 modulo 11. So we get x is congruent to 4 modulo 11. And we just have to solve that one congruence. There's not really much more to it than solving that one congruence. We have done this over and over again. I'll just solve it out for you real quick. So x is equal to 5k plus 3. If you sub that in here, we get 5k plus 3 is congruent to 4 modulo 11. And that gives you that 5k is congruent to 1 modulo 11. So we have to find the modular inverse of 5 modulo 11. Note that 11 times 5 is equal to, hold up, sorry, not 11 times 5. What? Okay, sorry. Okay. 5 times 9 is equal to 45, which is congruent to 1 modulo 11. So we multiply both sides of this congruence by 9, and we are left with k is congruent to 9 modulo 11. That's all good. So we can write k as 11j plus 9. And subbing it back here, that gives us x is equal to 5 times 11j plus 9 plus 3, which gives us x is equal to 55j plus 45 plus 3 here plus 48, which gives us the congruence solution. X is congruent to 48 modulo 55. And we have one more problem to cover before I end this lecture, and that is this problem. Find all solutions to x cubed minus x plus 1 is congruent to 0 mod 35. This is a challenging problem if you haven't seen something like this before, and you've got to use some intuition to actually solve this problem. So let's go ahead and solve it. As I said before, the best thing to do is split it into modulo 7, and modulo 5. Mod 7, mod 5. So first, let's actually find some solutions modulo 7 for what it works. And we only have to test the residues 0 through 6, since those are the only possible residues in modulo 7. So for 0, we'll make a table for this. We'll make this x and then f of x. And so if we do 0, we get 0 minus 0 plus 1. 1 is congruent to 0. That does not work. If we substitute in 1, we get 1 minus 1 plus 1, which is 1. That does not work. If you substitute in 2, we get 8 minus 2, 6 plus 1, 7. And 7 is 7 modulo 7 is 0. So that is very nice. That means it does work. Let's look at 3. That gives you 27 minus 3, 24, plus 1, 25, which is 4 modulo 7. That does not work. Also note that 4 can be written as negative 3, so we can make our computation a bit easier by just letting this be negative 3. So that'll give you negative 27 plus 3, because you're subtracting a negative. That's negative 24 plus 1, negative 23, which is negative 2 mod 7, which does not work. That's also a 5, if you're wondering. It's equal to 5 modulo 7, or equivalent to, I guess. We can go on with negative 2, since that's what 5 is congruent to modulo 7, to simplify our calculations. So that would be negative 8 plus 2 plus 1, which would be negative 5, which wouldn't work. And then we can substitute in negative 1, which is congruent to 6, which gives you negative 1 plus 1 plus 1, which gives you 1, which doesn't work. So the only residue that works here is 2 modulo 7. So we can say that x is congruent to, well, yeah, x is congruent to 2 modulo 7. Let's do the same thing for modulo 5. It shouldn't be too hard since it's only just testing up to 5. So let's take 0. That'll give you 1. Doesn't work. Taking 1 will give you 1, which doesn't work. Taking 2 will give you 8 minus 2, 6, plus 1, 7, which is 2 mod 5. Does not work. Taking, well, 3, which is also equivalent to negative 2 modulo 5. So we can actually say this as negative 2 now. That'll give you negative 8 plus 2, which is negative 6, plus 1, which is negative 5, which means it does actually work. And we can take negative 1, which is equivalent to 4. That gives you negative 1 plus 1 plus 1, which is 1. And that does not work. So the only residue here that works is negative 2. It is congruent to 3 mod 5. So x is congruent to 3 mod 5. Now we have a system of congruences, which we can easily solve. So let's just quickly solve through this. X is equal to 7k plus 2. Now what we can do is substitute this back here, which gives you 7k plus 2 is congruent to 3 mod 5, which turns into, since 7 is congruent to 2 mod 5, 2k, and we subtract by 2 here, it's congruent to 1 mod 5. As we have seen several times in this lecture, the modular inverse of 2 modular 5 is 3, so if we multiply both sides by 3, we'll be left with k is congruent to 3 modulo 5, which we can write as k is equal to 5j plus 3. All right, that's good. Oh, oops. That's an accident. So now we can substitute this back into our expression for x. So x is equal to 7 times 5k plus, no, 7 times 5j plus 3, and then plus 2. So that's the expression for x, which gives you 35j, that's a 21 there, plus a 2 is plus 23, which gives you that x is congruent to 23 mod 35. And that is your solution to that cubic in modular arithmetic, which is definitely weird, but once you work it out, isn't too bad. Thank you for watching. If you have any questions on the content in this lecture, please don't hesitate to join the Discord and ask us a question in math help on the Discord channel. If you're already in the Discord, we would appreciate any feedback on this presentation you have on suggestions. And I hope you have a great day. This is the end of the Modular Arithmetic lecture series, and I do hope you found it helpful.